Time is 4 o'clock. Let's get started here. So, project number 3 was graded since we last met. There's a few things I want to discuss about project number 3. So, in particular, problem 1G. So, what we're doing here is trying to determine if the variances that we're estimating through these 4 different methods, if they are actually correct. And we can make this evaluation through a simulation. In particular, what we're doing is this. We are calculating 1 over b minus 1 times the sum equal 1 to capital B TR minus T bar squared. Where B was, I think, 500 for this. Unfortunately, I didn't bring mine out. So B is equal 500. So what? So we calculate this particular value across all the different simulated data sets. And then we also calculate for a particular variance estimate of interest, calculate this. Where this is the estimated variance for, or statistic, for let's say the beef sample. So what you need to do is compare the two. And if they match, it says then that this estimated variance for T is correct. If they don't match, then it says that the estimated variance is not correct. So why can we do that? I don't think we ever talked about why. Yeah, law of large number plays a role here, yes. Let's first talk about what this, what I've labeled as number 1 here. What is this doing? Oh, I should draw an arrow there because I don't confuse you. This is a Monte Carlo estimate of what? Variance of T. And notice I'm not going to put a hat on top of the var. This is the true variance for the statistic. And as long as B is large, you know, this value that we get for 1 is going to be very, very close to the variance of T. And so this is what we're shooting for. This is the goal. Now, what is then this number 2? What is it trying to estimate? Not exactly variance of T. Notice I'm taking...
It's the average of the variances.
So it's trying to estimate the expected value of the estimated variance of T. Right? There's parentheses. So, and note that this expected value, I can take this expected value because the variance hat of T contains estimators, because it's an estimated variance. Now, what you would hope then that if you look at what this expected value of the estimated variance of T is, you would hope that it's close to the true value. If it's not, then it says, uh-oh, maybe this estimator that you have here, when I'm talking about the estimated variance of T, that estimator is incorrect. And so this is how in research you can make a judgment of, if this variance that you derive works. So it's a very, very useful tool. Any questions about that? Okay. So let's look at 1G part triple I. So what we have here are 4 different, average variances. 4 different averages of these bar hats. The first one's non-parametric delta method. The second one is jackknife. The third one is regression method. The fourth one is the bootstrap. Wow, take a look at the bootstrap. I'm sure all of you were probably surprised about that. But I have to admit I was a little bit disappointed that no one, at least in their project, decided to look into why is this occurring? Why is the bootstrap so different from all the other ones?
I didn't.
What's that?
I did, because I was like, what the hell? I just didn't talk about it.
Okay. Well, that's good. I'm sure all of you were thinking that too. But you just didn't want to necessarily put it on there because, of course, that gives me an opportunity to take off points if you put anything extra down. I understand. But obviously, if you have something that's very higher than what you expect, you might think, okay, well, maybe I have some extremely large values, so I could take a more robust estimate of middle, and that's what I did here for median. And look what happens here. This is at least more reasonable. And if you go further and actually take a look at, well, let's say how often do I get a bootstrap estimate greater than 10? Only 5 times, but we can see that, especially a few of these times is extremely large, and that's going to really, really weight or really cause that mean to really go up. But so, it's interesting that happens. And what one could do is maybe further investigate this. What I would expect is if you look at the actual data, you would probably find certain values are showing up a lot, and that's causing this. I did not go that far, because then I was getting into more of a research problem versus an actual just simple problem that we're doing for a homework or a project, I guess in this case. So that's why I didn't look into it further. But it will be interesting to do that to see if that is truly the reason, or if maybe something else is occurring. But I don't know what else would be occurring off the top of my head. So yeah, I was surprised when I first saw this myself when I was writing up the project. But one reason why I obviously had you still do this was because I wanted you to make sure that you understand that, while the bootstrap's great, or even the other estimators are good, are interesting ways to estimate a variance, you don't get something for nothing. We only had sample size of 10. When we now go to sample size of 100, we can see everything's working out. This is the Monte Carlo estimate of the true variance. Here's what these are doing. Averaged over the 500 data sets, you can see you're getting right on. So that's good. I guess also I should mention, too, going back up here to when we were using sample size of 10. Some of you said, oh yeah, the non-parametric delta method's doing good. But you got to realize that the true variance is 0.05. So what this is saying is that this is still a 25% underestimate of the variance, which is usually better to have an underestimate or overestimate. Over. Why? So you don't over-reject if you're doing hypothesis testing, or maybe your confidence interval is actually more narrow than what it really should be. Your true confidence level is a lot lower than what it should be. So typically we would prefer to be conservative. If you had a choice between a variance that's too large and a variance too small, you take the one that's too large. Not as large as the bootstrap, but the jackknife or the regression method. Well, definitely the jackknife would be preferred. or non-parametric delta. Okay. So anyway, kind of an interesting project. Are there any questions about the project? Okay, let's move on. Let's take a look at the calendar once again here. So I intend to give you project number 4 next time. Hopefully I'll have that posted by Wednesday evening. It's written, but there's one part I haven't decided if I'm going to include or not. Project number 4 is primarily just on the non-parametric bootstrap for hypothesis tests. That's section 4.4. There's a small part of it that talks about permutation tests, which is section 4.3, which we had just barely got into. In order for you to do the project, obviously, then you need to have section 4.4. Also, you're going to need me to go over this document here regarding the seminar that I gave a few years ago. Because in this project, then you're basically implementing the stuff I'm going to talk about in the seminar, which is a non-parametric bootstrap technique. So because of that, what I decided to do here is temporarily skip section 4.3 and go now to section 4.4 so that you can get started on the project after we do the stuff on Thursday, and then we'll obviously set a due date for the project, and I should then have enough time to grade the project to give it back to you so you have some feedback before our test number 2. So please turn to page 441 then in the notes. There will be a few times where we will have to actually turn back to section 4.3 to explain a few small things, but it's not going to be that bad. Okay. So with the non-parametric bootstrap and hypothesis tests, similar to the parametric bootstrap, we need to take our resamples from f hat 0. So in this case, that's the EDF, but adjusted so that indeed HO is true for the EDF. This makes this often difficult, unfortunately. A lot more difficult than the parametric problem. So let's take a look at some examples. So let's say you want to do a hypothesis test for one mean, the very first hypothesis test you probably ever learned. And so we're testing mu is equal to mu 0 versus mu does not equal mu 0. We do not resample directly from the Y's. Instead, we resample from an adjusted version of our Y's. Let's call them Y tildes. Where what we do, first of all, is take Y to Y minus Y bar for all your observations. So what happens then to your data then, this YI minus Y bar? What is that going to mean? It's centered at 0. So the mean of YI minus Y bar is going to be 0. If the hypothesized value of the population mean is mu 0 then, what we can do then is just simply add mu 0 then to every single one of these mean adjusted values. And now these Y tildes have a mean of mu 0, and thus F hat 0 corresponds to a distribution as a mean of mu 0, and thus you now resample from the Y tildes to resample under the null hypothesis. Okay, so that's not too bad. Makes sense. Let's look at a hypothesis test for the difference of two means. So this is maybe perhaps the second hypothesis test that you ever did. Mu1 minus mu2 is equal to 0 versus not equal to 0. Let's take a look at approach number 4 first, because this is a direct extension to the test for one mean. So now what we're going to do is form Y tildes again. And let's let Yij be basically the response from population I, and it's the observed value J. So I is population number, J is the index for the sample value. So again, what we're going to do is adjust our data so that it has a mean of 0. And now, instead of adding mu 0, which we don't have here, because remember what we're basically saying under the null hypothesis is that mu 1 is equal to mu 2. How about now we add y bar, the mean of all your observed y's? Because what this does, it says, okay, if these two means were equal to one another, well, what should it be? Well, the observed mean combined, all the data y's. And so now what we can do is do one of these stratified resampling approaches that we saw back early on in Chapter 3, where now that we have these modified data values, we can now resample from the y tildes for population 1, independently of resampling from the y tildes for population number 2. That's how you can do it. Well, there's many, many other different ways to approach this problem. Let's look at the first approach. This is on page 42. This again goes back to something from Chapter 3. What you could do is assume that your data actually comes about in this form. Y sub ij is equal to mu sub I plus sigma sub I epsilon sub ij. Remember that from Chapter 3. Notice this does not assume a particular distribution. What it does is it is a semi-parametric. So maybe you should call this a semi-parametric bootstrap than a non-parametric bootstrap. So it is making some assumptions, but not necessarily full-blown parametric stuff. So if you assume that your data comes about this way, and you say the null hypothesis is true, then that means then that the data actually comes about this way. Y sub ij is equal to mu, one overall mean, plus sigma I times epsilon sub ij. Then what we can do, just like in Chapter 3, form what are essentially studentized residuals, where this mu hat, and I just use mu hat here, essentially what I'm saying is y bar, so the average of across all the y's. Take these as your E sub ij's. When you resample from all the E sub ij's, notice you're not doing stratified resampling in this case. You're resampling from all the E sub ij's since they have the same distribution. Then we call our resample values epsilon stars. Using the epsilon stars, you find y stars. And those are your resample values. Notice mu hat's in there. Alternatively, what you could do is just assume mu hat's equal to 0. It's not going to change things. The reason being is because any kind of statistic that you're going to use typically to test HO here, it's going to be some form like this. So no matter what mu is, it gets canceled out between the two. So that's why it's not a big deal. So that's another approach. I guess, approach number 2 here, third one that we talked about, is obviously, this is an assumption for a model, but there's other kinds of models out there that one could use too. Just try to use that. And lastly, approach number 3, which is different from the other ones, but also makes some assumptions. What you could do is basically put all of your observations together into, let's say, one overall sample. And then resample, let's say, N1 values from this grand set of observations, and call that now a sample from population 1. Then resample N2 values, call this a sample from population number 2. That's how you find your Y stars. Now, why, in that case, are we resampling under the null hypothesis?
You're assuming that their means are equal and combine them together from one population.
Yeah, and that's the key thing. You're assuming that there's one population. So in other words, the distributions for the two populations from which the samples actually came from are the same, except for possibly a different mean. So notice again how this is, more of an assumption here. We assume that the distributions are the same. Obviously, this is not fully parametric, but I'm going to put it in parametric context. But you're basically saying population 1 is normal with the same variance as population 2, which has a normal population with the same variance. So essentially, you're assuming all moments are the same for the two populations, except for perhaps the mean. So, that is an assumption. Maybe sometimes it's reasonable, maybe sometimes it's not. We will talk about this approach a little bit more when we do permutation tests in section 4.3. So how can we calculate a p-value? Same as what we did before. So let's call p-boot our p-value. And all you're doing, if let's say large values of t indicate evidence against the null hypothesis, you look at, is the probability of t star greater than or equal to t given f hat? Or find that probability, I should say. Small values indicate evidence against the null hypothesis. So essentially what we're doing, in a regular old situation before you got into this class, if this was your null hypothesis, your distribution of your null hypothesis, if you were to calculate a p-value, all you would do is find the area underneath this curve. Now with the Bootstrap, what we're doing is that we're going to try to estimate that by taking resamples, maybe have a histogram that looks like this, and simply find the area again to the right of what your test statistic is. How do we find that? Well, we have this nice little equation to find the, basically, essentially what it is, the proportion of the t stars greater than or equal to t. Now note here, I put a p here instead of p-boot. I would prefer to call this p-boot, but I was just being consistent with the notation in our book. They just call it p. I don't know why they don't call it p-boot, because if you look in the book, they call this p-boot. So I think it's a problem with their notation, but I just stuck with it. I think they're trying to emulate what they did with the parametric bootstrap. They called it p at that point. But why do they call it p-boot otherwise? I don't know. Anyway, it's just notation. What happens if we have maybe a situation where in large values or small values of t indicate against the null hypothesis? So in this case, you have a two-sided test. We do exactly the same as with the parametric bootstrap. We look at how extreme is t on the left-hand side or on the right-hand side of the distribution. If it's extreme, evidence against the null hypothesis, we have a small like that. Okay. So, now we're going to talk about an actual numerical example. For those of you who have me for Stat 875, this data set should look familiar. The Larry Bird data set. Probably thought you'd never get to see it again. Ha!
I use it in 218 all the time too.
Oh, good. It's a great data set. Great data set. I remember when I first found this data set, it was probably about 1995, 1996. I was teaching a course like Stat 218 here, like the Stat 218 that we have here. I guess obviously it was at Kansas State. And we would have weekly GTA meeting. So all the teaching assistants would get together, and our professor who was leading us would expect everyone to pick a topic that they would present to all the TAs to describe how you would teach a particular area. And I happen to have regarding a topic on independence and stuff, so I found the Larry Bird data set. Even to help demonstrate it to the other TAs, I actually brought basketball and simulated shooting free throws in the classroom. Fortunately, the ceilings are not very high, and I accidentally hit a tile. Anyway, fortunately I didn't break it. Okay, so this is the Larry Bird data set, and I realize that there's a number of you who probably have not seen it before. So I describe it on page 427. So we're also going to do permutation tests. So in basketball, free throws are typically shot in pairs. Not always, but most often you're going to shoot one free throw, and then you're going to shoot another. And so you might think that, what happens on the second attempt might be dependent upon the first attempt. So, let's say Larry Bird, shoots his first free throw and he misses it. And then that might psych him out thinking, oh, I'm so bad, I'm such a bad basketball player. I have no chance on this second free throw. And so maybe his probability of success is lower after missing the first. And vice versa, if he makes the first, that might give him confidence then on the second free throw, and his probability of success might be higher. So what we're looking for is dependence. Is there a dependence between what happens on the first attempt versus the second attempt? And what we have here is data from 2 different seasons. And we're going to let X denote first attempt, Y denote second attempt. And so, for example, 251 times Larry Bird made the first free throw and then made the second free throw. 34 times he made the first but then missed the second. 5 times he missed them both. And so what we'd like to do is be able to actually do a test. Are the first free throw and second free throw outcomes independent of one another? And this then leads to what most of you probably seen in another class before, even if you didn't take steady 75, a Pearson chi-square test for independence. So our hypotheses can be formed like this. The probability that X is equal to I, meaning row I, let's say row 1 or row 2, so this would be like I equal 1, I equal 2, and Y is equal to J, so this would be J equal 1, J equal 2. That joint probability is equal to the product of the marginal probabilities. This null hypothesis means independence. So it doesn't matter what happens jointly. What only matters is what happens marginally. The alternative hypothesis, well, guess what? They're not all equal, so you do have dependence. So alternative is dependence. To put it another way, in commonly used notation, we can let pi sub I j be this joint probability. Pi sub I plus is marginal for x, pi sub plus j is marginal for y, and you can write hypotheses such as this. Okay, so how can I now enter this data into R? There are ways in R that you can actually represent contingency tables. You can't really do that in SAS. But what we can do is use what's called the array function. An array is a data storage. Think of it as a data storage device. You can have 2-dimensional arrays, which is a matrix, 3-dimensional arrays, 4-dimensional arrays, and so on. You can think of each dimension then as a dimension of a contingency table. So I'm going to use, in this case, we have a 2-dimensional array. Say array, I put in my data, and in R you have to put in the columns first. So if you notice, the first column is 251 and 48. I don't worry about, you don't have to put in marginals. So I can put in the marginals of the table. The second column, 34 and 5. Dimension of the table, 2 rows, 2 columns. Dimension names of the table. The row variables is called first free throw. Either you made or you missed it. The columns, second free throw, made or missed. I'm going to put that in an object called n.table. Call it something else. I just decided that one because n's often used to denote counts. And so there's my contingency table. Okay. So if I want to, I can actually access parts of the contingency table by saying n.table bracket 1, comma 1, and of course I get the first element, or the row 1, column 1. Now there's another way to represent this data. I call it the raw data form. That can be very helpful when we're doing the Bootstrap. And I'm going to show you the data first and then explain what it is. So if you remember, so there's 251 times Larry Bird made the first and made the second. What I can do is create a column in a data frame, or in this case it's a matrix actually, create a column that represents what happens on the first attempt. Did he make it or miss it? I'm going to give it a value of 1 if he made it, 2 if he missed it, for row numbers. Also, I'm going to create a column that represents what happens on the second attempt. If he made it, a 1, if he missed it, a 2. So what we have here are 251 different 1-1 pairs. We will have 34 1-2 pairs, 48 2-1 pairs, and 5 2-2 pairs. And you can see these 2-2 pairs. The total number of free throw pairs we have in the contingency table is 338. So you see 338 rows to this data set. So the reason why it's called what I like to call the raw data is because this is how the data probably would have came in an actual application. Larry Bird goes out and shoots a pair of free throws, and it's recorded as made or missed for the first attempt, made or missed for the second attempt. And then the second row represents what happened on the second pair of free throws that he shot. So a raw data format. And what I showed you at the beginning on page 427 is kind of the summary of all the raw data in a contingency table form. Okay. So how did I form the raw data? There's a number of ways that one could do it. This is just the way I did it. I used the matrix function. I said data equal NA, number of rows equals 0, number of columns equal 2, just to begin with. I put that in an object called all.data. And then I simply loop over all my rows, all my columns. So n row gives me the number of rows, n column gives me the number of columns. And then I use the rbind function that combines together what was in all data before, and then an additional matrix which represents the row number and the column number corresponding to the number of observations that had that. Would anybody like me to go into more detail than that? Okay, I'll just leave it at that. Again, if you have problems understanding this aspect, just run it yourself. You maybe put a print statement here so you can see what's happening on every stage of the loop. Then there's a function R called xtabs for cross tabulations, if you've ever heard of that term before. That's going to take this raw data and put it back into a contingency table format. I only did this just to verify that indeed this matches what I had before. Notice the syntax. All I do is I say tilde, my row variable plus my column variable. So again, the way that we would typically approach then answering this hypothesis test problem is to do a Pearson chi-squared test for independence. I expect all of you have seen this before, but let's just take a look at the statistic. So x squared is equal to, I sum over the rows, I sum over the columns of my table. take the observed value for a particular cell, so n sub ij is the row I, column j cell count, minus what I expect that cell count to be if the null hypothesis was true, which is the row total times the column total divided by the total sample size. I square that, and then I take it divided by the estimated expected value of the null hypothesis again. Perhaps you use different notation to what I'm presenting here, but this is essentially it's the same thing. So you could say observed minus expected squared over expected, and that's what you're doing for every cell in the contingency table. Okay. Now, what you typically do then, get the test statistic and you compare it to a critical value from a chi-square distribution. R minus 1 times C minus 1 degrees freedom. Why? Because one can prove that x squared converges in distribution to a chi-square random variable with these degrees of freedom. It's just a proof. So I already talked about the critical value. Then the p-value, of course, would be the probability that this random variable, let's say a, is greater than the observed value of your test statistics. That's why I use a little x squared. That's your p-value. So only large values indicate evidence against the null hypothesis. Now, remember that this chi-square distribution here is the asymptotic distribution. X squared itself does not have a chi-square distribution. For a very large sample size, it's pretty close to chi-square, but it does not have exact chi-square distribution. So you might be wondering, well, how large does n have to be in order for you to be comfortable with using a chi-square approximation? There's not necessarily one specific rule I can give you of when n is large enough. Typically what you see is something like this. If your cell count or your estimated expected value for a cell count, if it's greater than 1, you're safe. Some people say greater than 5, you're safe, using the chi-square approximation. Take a look at my data here. We don't get a 5 there. So, if Larry Bird would just miss more free throw pairs, we wouldn't have to worry about this chi-square approximation. But we have a 5. So you might be questioning, well, is this chi-square approximation actually working or not? And that's where the Bootstrap is going to come in shortly. But let's actually look at how one would actually perform the tests without the Bootstrap. There's a few different ways. One way is to use the function called chi-sq.test, for obvious reasons. You just simply put in your contingency table, say correct equal false, or you can just say F there. By default, R will actually put a correction, or I should say, without getting all the details, it actually will change the test statistic a little bit to try to make this chi-square approximation work better. There's no reason for the correction anymore, so we can use the Bootstrap or permutation test, but that's what it does. So that's why. So we get the exact test statistic. That's why I say correct equal false. So my test statistic is 0.2727, 1 degree of freedom. P-value is 0.6015. So if I can trust this chi-square approximation, I would say, well, there's not sufficient evidence to indicate problems with, there's not sufficient evidence to indicate defects. Okay. So let's talk about how we would approach this problem with the Bootstrap. So let's go back to page 445. Well, interestingly, since I was going to do categorical data analysis for my dissertation, it was going to involve some Bootstrap techniques, my advisor decided to put the problem on my PhD comprehensive exam, which asked, how would you approach a problem like this? So there are actually two different ways to do it, and this is what I wrote down. I got 100% of this problem, so this isn't right. Just an interesting side note, because I'm just thinking back to the day when I was taking my PhD comp. It's interesting to see how things have changed over time for PhD comps in statistics. The typical PhD comp in the statistics department, including the one that I had at K-State, involved, and I'll just give you the exact form of the K-State PhD comp, involved a whole day test on your PhD theory courses. So this was 2 advanced inferences and 2 asymptotics courses for me. That was one day. And then 2 weeks later, you come back and you take another all-day test that was over 4 PhD level classes of your picking. So 8 courses total. I actually counted the number of hours I studied for my PhD comp exam to make sure I studied enough, and it was 600 hours. Give you some perspective. And it wasn't just K-State who was doing this, it was other stat departments were doing it. And also this was, you couldn't take the exam until your 5th year of grad school. So you couldn't really start your dissertation research until your 5th year of grad school, until you passed the exam. Anyway though, K-State and other schools have made changes so that students can, say, get to the research sooner, and so that you don't have to spend so many hours studying for these exams. And typically the norm that I find out in other departments of statistics is that you do what's essentially a dissertation proposal, where you maybe have written 1 paper for your dissertation, and you're proposing what you're going to write for the other, typically 2 other papers for your dissertation. You present that to your committee, and you also do a public seminar on it. Here at our school, we're more, it's more up to the advisor what exactly you do for your PhD. At least for my PhD, since I haven't do a dissertation proposal. Anyway, though, so here's how you could actually approach this problem from a Bootstrap perspective. 2 different ways. You can independently resample with replacement the row numbers and the column numbers in the raw data from the raw data form. So you independently resample, and then you put the row numbers and column numbers basically back together to form a data frame, you could say. And then from that, calculate x squared star. Now, why does this work? So to make sure it's clear how this resampling is done, I'm going to probably add this to my notes next time. Let's say that we have a very simple raw data set. So just have 4 observations. You have 2 observations that are in row 1, 2 observations that are in row 2. You have 3 observations that appear in column 1, 1 observation appearing in column 2. So if we look at a contingency table form of the data, so we would have 2 here, 2 here, 3 here, and 2 here. Oops, 1. This is what it will look like. I think I should be able to fill this in. Yeah, that works. So that's my raw data. And now under the Bootstrap, then, going to resample from the row number. So maybe for a particular resample, you may get, let's say, 1, 2, 1, 1. And for the columns, maybe you get 2, 2, 1, 1. And from that, you can form x squared star. So notice how there was no row 1, column 2 observation in the original data, but in my resample data, I do have one. Okay? Because I'm independently resampling from the row numbers and from the column numbers. Why am I? How is this resampling under the null hypothesis?
Because under the null hypothesis, we have independence, our margin means form or something, basically.
Essentially, I mean, what we're doing is when we're taking the resamples, if we were resampling under dependence, what we would be doing is resampling pairs, right? But we're not. We're saying if the row and the columns are truly independent, what happens for the rows is not going to happen, or it's not going to depend upon what happens in the columns. So let's just resample from the numbers independently of one another. It's going to be interesting to look at this on the video as I talk with my hands. We're resampling independently. So that's why this works. What could be a potential problem, too? This is going to foreshadow something coming up. There could be a potential problem to resampling in this form, especially with such a small data set. I think what you're basically saying is what happens if we get everything, let's say, in row 2, right? Maybe you get everything in row 2, and you have no row 1 at all. So, your contingency table has just changed form. We'll talk about how that can be a problem coming up. Okay, so that's method number 1. How can we code this in R? Let's actually talk about that. Especially for hypothesis testing, oftentimes it's easier to do the coding without the boot function because you're having to change the form of that hat. But you can still use the boot function in this particular case. And what you would do is this. I don't know, maybe there's a different one, but this is the way I do it. What you could do is create a data frame that contains a variable called index. And what I'm going to do is put for the first 4 rows of index the row numbers, and for the last 4 rows of index, put in the column numbers. And then I'm going to form a new variable, for lack of a better name, let's call it table.part. That helps you know, is this corresponding to the rows, or is this corresponding to the columns? So X's or Y's. And then what you can do is use stratified resampling, like what we did at the beginning of Chapter 3, where your strata is table.part, and the boot function will take your resamples within, take the resamples of index within each table.part. That's a nice way to do it, but I don't know, maybe it might be easier just to use the sample function yourself and do it without the boot function. Page 446. Another way is actually to take advantage of the multinomial distribution. And that is you could find the estimated expected counts under independence. Mu hat sub ij is equal to ni plus times n plus j divided by n. And then find then what will be the estimated probabilities under independence for each. Think of categories that we have in a 2x2 table. We essentially have 4 categories. You're following one of 4 cells. So look at pi hat sub ij under the null hypothesis, and then use a multinomial distribution. Just take your examples. So that's it. There's a function R called R multinom that allow you to do it. So we're not doing a parametric bootstrap here. It just remember the relationship that we have with bootstrapping and the multinomial distribution that basically allows this idea. Okay. And I have here, be careful. This is what I was getting at. Perhaps I could have just waited until now. Oh well. With both of these approaches, one needs to perform some sort of conditional resampling approach to make sure that your contingency table does not change size. Well, why? Remember that x squared, our Pearson chi-squared test statistic, is essentially an asymptotically pivotal statistic. So that's good. We want that. But remember what happens to degrees of freedom when the number of rows and number of columns change. So let's say in a particular situation that you have a 3x2 contingency table that you observe. And let's say a particular resample comes about such that now you have a 2x2 contingency table. So what that's saying is that the asymptotic distribution is changing. And so your bootstrap distribution in some respect will change then as a function of it. That's a problem. Because now you're going to have some x squared stars that are going to have one particular distribution, and then some x squared stars that are going to have a different distribution, but you're actually wanting to combine them all together to do the tests. So it's better in these kinds of situations to perform a conditional resampling, where if you have some resamples where the table size changes, throw them out. Only look at the ones where you have a full table size. Of course, what happens then if you start having to throw out a lot of contingency tables? Maybe the bootstrap is not the approach you want to use. Instead, a permutation test would actually avoid that problem, and you'll see why it does later. Okay. So let's do the test. So I need to form my data set in the correct form so that the boot function works with it. Sorry, I've lost my program. Yep. So what I need to do is find a data frame. I'm going to create my index variable that contains all my row numbers, and then table.par is equal to x. Do the same thing for the column numbers. R bind them together, and this is what we get. So notice I have 676 different rows to this data frame, which is 338 times 2. Now I need to write a function that's actually going to find my x squared star. So again, I'm going to call it calc.t, pass in my data, my indices. The data is in a data frame, so I say D gets data, bracket I, comma, in bracket. I pull out all my x, all my row numbers. I pull out all my column numbers and put them in objects x and y respectively. Then I use the chi_sq.test function. I might have actually skipped over this earlier when we were just doing a chi-square test with the bird data. Before we said chi square chi_sq.test parentheses n.table. Instead, what you could also do is put in all the row numbers, put in all the column numbers, essentially work with the raw data, and do the test that way with chi_sq.test. I'm sure it's in my lecture notes how it was done originally with bird data. You can take a look at that. And I'm going to immediately pull out just x squared, the test statistic itself. So there's a component that's returned from this object that's called statistic. That's my x squared. But then an object called x.sq. And then at the very last part of my calc.t, I return my x squared. And I'm also going to do something else. I'm going to check my table size. So what I've done is written a function called check.table. That checks to make sure that I have 2 by 2 table. How do I do that? Simply pass in my data, pull out the x's, pull out the y's, the row numbers and the column numbers. Then I use x tabs to find my table. Count the number of rows, count the number of columns, and return it. Let's try this with the observed data. And I get my x squared 2 by 2 table. Excuse me. Without getting all the details, I'll let you read that little note at the bottom, page 48, about problems that can occur when you only have a 2 by 2 table. Page 449, then let's actually do the Bootstrap here. So I'm going to set a seed number, we use 999 resamples. Now, remember, if we talked about this before. What do you think for using about 999 resamples for hypothesis? Is that enough? Think about what we're trying to do here. We're trying to get a p-value. And, it depends upon what the p-value truly is. If the p-value is large, let's say 0.5, well then no big deal, because you're in the middle of the distribution. But if p-value is small, you're on the edges of the distribution, and we know that estimating stuff on the edges of the distribution can be difficult, so you would want a larger R. So if I had to do this over again, I'd probably use a larger R. But in this particular example, we do have a high p-value, so I'm still okay. But again, generally speaking, use a little bit larger R. Okay, so I use my boot function, data equals set1, statistic calc.t, resamples, non-parametric bootstrap, strata equal set1 $table.word. So let's run this. Yeah.
Maybe you have only one statistics, right? If you want to make
well, I'm just doing x squared, but I'm also keeping track of the number of rows and number of columns too. So I'm actually returning 3 different things in calc.t. Okay?
if you want to make it help with statistics,
If I want to do what?
if you want to help with multiple statistics,
well, just make sure everything's embedded inside your calc.t so that all the statistics are returned in the end. So if you notice here, here's my x squared. This other stuff here is not meaningful anymore because remember we're taking resamples with respect to the null hypothesis. Notice here I have 2.0 for the last 2 statistics, and I have a bias 0, standard error 0, which basically means every single table is 2 by 2. Yeah. Yay. Yes, I was happy about that because the alternative can be messy at times. Let's do a plot of the distribution. So I say plot boot.res like before. And just to show you that what else you can do with this generic function, or its corresponding method function, I say qdist equal chi-squared. Because you can actually do the QQ plot using a chi-squared distribution instead of the usual norm by default. You can also specify the degrees of freedom. And this is what we get. So note that this will be a chi-square 1 for this particular case. And we can see, with the QQ plot, chi-square 1 looks okay. So even though Larry Bird missed both free throws 5 times, it's not enough to really worry about the distributional approximation. I mean, sure, we have 3 values at the end there that are kind of streaming off, but remember, this is the extreme portion of the distribution. It's a heavily right skewed distribution. So you're going to have troubles estimating what we like to 0.999 quantile. So I'm not worried about that at all. So that's good. Let's calculate the p-value now. So similar to what we did with the parametric bootstrap, what I do is I sum up all my x squared stars. How many of them are greater than or equal to x squared itself? I add 1 to it, divide by r plus 1. I get 0.639. So using the chi-square distribution approximation, we had 0.6015, quite close. And this is to be expected because we saw that the chi-square distribution approximation seems to work. But a little bit of a side note here, and I think we've kind of addressed this before. And I've actually seen this in statistical research papers where they derive some kind of distributional approximation, and for a particular data set that they're trying it out on, to help verify that indeed their distributional approximation works, they use the bootstrap. And they show, oh, look I'm getting the same results with the bootstrap. Or, if I plopped a chi-square 1 approximation on this histogram, oh, look it's just about the same. Therefore, my statistical methods I'm proposing work. So, the bootstrap obviously can be used to do the test, but it can also be used as a research tool in these kinds of situations to make sure that what you're doing does work. Okay, so that takes us to page 450. So, as another way to check, are you having any problems with your contingency table size? What you could do is just simply check all the number of rows that I get for every single resample. How many of them are not equal to what was actually observed? So this value on the right is 2. I sum them all up, so I get a bunch of trues and falses. I sum them up. The trues are converted to 1s, falses are converted to 0s. And look at this, all 0s. Same thing for columns as well.
What's the 2?
Sorry. If you look back at the check.table function, the first thing that's returned is the number of rows selected. Sorry. You could also look at a table that results from this resampling, a contingency table that results from these resampling. Remember how the boot.array function allows you to actually look at the resamples? I'll let you look at the code itself. Let's just focus on this. So this is the third contingency table that's found from these resamples. And again, we can compare that to what was actually observed. Eventually, I'll get there. There we go. Okay. So you can see that obviously they're different. That's kind of the purpose of me doing that. But what I also want to point out is this. Let's take a look at the margins. Let's see, this is 285, 288, 50, 42, and 296. Notice how the margins are different. And this is actually where the bootstrap have problems if any of those margins are 0. With a permutation test that we'll look at, not next time, probably actually, no, maybe next time. The permutation test will always have the exact same marginal totals.
Rewinding just a second. Just a little. Right there. Where you did where you checked whether or not your contingency tables have the right size. Could you use your boot.res $T0? The second one of those?
Oh, yeah, you could. You could.
Since you actually
Yep.
return those there.
Yeah. Yeah, so you could do that. So, we could do the usual kinds of plots, other plots too, in terms of, the code's in the program, since we've done this before. We do the histogram, put a chi-square 1 distribution approximation on it using the curve function, use the AV line function, put the observed test statistic value, and obviously you can see it's not extreme on the right side. And we're going to again look at an EDF of the x squared stars, put a chi-square 1 CDF on the plot, and you see it matches very well. Okay, let's take a look at another example. So this is an example of where the Bootstrap does fail. This data set's located on page 436. You don't necessarily need to turn back yourself, so I'm just going to quickly show it to you. So, I entered the data in the same way as before. Call it n.table once again. And you can see it's a 3x9 contingency table. It's not real data. It actually comes from Gressy's 1996 book on categorical data analysis. The key thing to look at there is notice all the zeros and the very low cell counts too. And whenever you have low cell counts, that gives somebody who's doing categorical data analysis gets a little worried, because then chi-square approximations will not work. In fact, you'll see later when we do a permutation test with this, definitely chi-square distribution approximation does not work. And so you might, be worried about that. You might want to implement, let's say, the Bootstrap. But the Bootstrap actually does not work in this case. Let's actually run it. So basically, it's the same code as before. So I won't go into all the details of the code. Let's see here. So my x squared itself, my observed data, is 22.28. So that's kind of large. 3x9 table. One thing that I failed to mention with the bird data that happens here as well is that you're going to see warning messages like this. By default, with the chi-sq.test function, R will always print a warning message if mu hat ij is less than 5. So don't worry about that warning message, but that's what's happening there, and that's why you see those warning messages. I just fortunately failed to mention it before. So let's look at how many times my number of rows does not equal 3. Once. Number of times my number of columns does not equal 9. 991 times out of 999 resamples. Oops. This is a problem. Yeah, hopefully I have 8. Maybe I have
Maybe 7.
Yeah. So that's why the Bootstrap's not working. So also, how would you go about, let's say with the Larry Bird data set, we did have some problems. And maybe 5 data sets did not have a 2x2 table anymore. How would you actually remove those particular, let's say, contingency tables from your analysis? What would you do? Remember, we're trying to find a p-value. So actually, let me find code where we did the p-value. So here's how I calculate the p-value. Now, if there were some X squared stars that came from tables that were not 2 by 2, I would want to remove them. How would I go about doing that?
Would you put another check within your sum, say and your size is the right size?
Yeah, you could. You could do another check. I think alternatively, maybe a little bit easier would be this. Somehow specify the particular rows that are okay, and just return those rows. There's a variety of ways you can do that. I'll let you figure that out on your own.
Would you still divide by r plus 1, or would it be r
Yeah,
minus the number that you...
Yeah, so you would need to change r here. So you might want to count then the number of cases that you're including. Thank you for pointing that out. So you just somehow need to get some trues and falses in here. So you just return the true rows. They're the contingency tables that work out. Change r, and you're okay. Now for an actual, let's say, paper that you're writing, let's say you want to include an analysis like that in there, you do need to state that, okay, I had to throw out five contingency tables that didn't work out because of this reason. Now, if you're throwing out 500, then again, you might want to rethink using Bootstrap. As long as you're not throwing out too many, you'll be fine. Okay. So the next thing that we're going to do is this. We are going to go through this presentation that I made in probably February 2003 when I came up here to interview for the position. I was actually a professor at Oklahoma State at the time, but when I heard that Nebraska finally was going to form a Department of Statistics, I heard this in 2002, now's my opportunity to come back home to Nebraska. I never thought I'd be able to come back home to this regional stat department here at the time. So I didn't go here for grad school. And so I thought, well, that's great. And fortunately, Nebraska hired me, and I was able to get faculty football tickets too. Because after all, that's the most important thing. So anyway, we'll go through this presentation. I kind of debated if I wanted to give you the actual whole presentation, but I know that some of you probably were interested in going into academia. Whenever you go into academia, you're going to have to give an interview seminar. And so I thought, well, here's my actual whole seminar. Here's an example of how to present it. We will not go through every single slide that's in the presentation itself, but we will go through enough of them so you understand what the statistical method is that I'm doing, and also, in particular, the Bootstrap portion. For project number 4, what you're going to be doing is implementing the Bootstrap portion of it yourself. I'm not going to give you any code for how to do it. You got to figure out the code yourself. Okay, we are out of time. Are there any questions? Okay, that's it for today.